A line of subtle movement is unfolding far beneath the Pacific, and the signals are difficult to ignore. Why are dozens of tremors clustering so tightly in one offshore corridor? What forces are driving repeated shaking at nearly identical depths? And why is this activity appearing in a region long known for producing some of the most powerful earthquakes on Earth? Over the span of a single day, a sequence of earthquakes began rippling through the seafloor off the coast of Washington. The pattern was not defined by a single dominant shock, but by repetition, event after event, each striking within a narrow geographic band, each occurring at roughly the same depth of about 10 kilometers, or approximately 6.2 miles beneath the ocean floor. The magnitudes ranged from modest levels in the high 2 range to more noticeable events exceeding magnitude 4, with the largest reaching magnitude 4.2. The timing of the sequence reveals a persistent and structured progression. The earliest recorded tremors began shortly after midnight, coordinated universal time, and continued steadily through the morning and into the afternoon. Within that window, multiple earthquakes above magnitude 3 were recorded, interspersed with smaller events that filled in the gaps. Rather than a random scatter, the activity formed a clustered swarm, an indication that the underlying cause is not isolated, but systemic. Geographically, the tremors align along a section of the ocean floor associated with a spreading center where tectonic plates are gradually moving apart. This area is part of a broader geological framework that connects directly to one of the most closely watched fault systems in the world. The seafloor in this region is not static. It is continuously forming, shifting, and migrating. New crust emerges where molten material rises, cools, and solidifies. Over time, that newly formed crust is pushed away from the ridge, moving slowly but persistently toward a convergent boundary, where it is eventually forced beneath a continental plate. The depth consistency of the events is particularly notable. Nearly all recorded tremors in this sequence occurred at approximately 10 kilometers below the surface. This uniformity suggests that the earthquakes are not occurring randomly throughout the crust, but are instead confined to a specific layer where stress is accumulating and being released in repeated increments. In many seismic sequences, varying depths can indicate multiple fault structures or different stress regimes. Here, the near-identical depth points to a singular mechanical process driving the activity. Magnitude distribution adds another layer of significance. While the majority of events fall within the magnitude 2 to 3 range, several have exceeded magnitude 3, and multiple have approached or surpassed magnitude 4. In seismic terms, this elevates the swarm beyond background noise. Microseismic activity typically consists of very small events that rarely exceed magnitude 2. The presence of repeated magnitude 3 and 4 earthquakes indicates that larger segments of the crust are being affected, releasing measurable amounts of energy. The coordinates of these tremors place them well offshore, far from population centers, but directly within a region that plays a critical role in regional tectonics. The ocean floor here is part of a dynamic system where divergent and convergent processes operate in tandem. As plates pull apart at the ridge, they create new material that is eventually transported toward a subduction boundary. This continuous cycle introduces stress not only at the point of formation, but along the entire path of movement. What makes the current sequence stand out is not just its presence, but its location within a segment that has shown relative quiet in past decades. Historical comparisons indicate that while northern portions of this offshore system have experienced intermittent clusters, this central section has remained comparatively inactive. The emergence of a concentrated swarm in this area marks a departure from that pattern, raising questions about what has changed within the underlying structure. At the same time, deeper processes are unfolding beneath the surface that do not always produce traditional earthquakes. Tremor activity, distinct from standard seismic events, has been elevated across a broader region extending from northern California through southern Oregon and into areas near Vancouver Island. These tremors occur much deeper within the Earth, along the interface where one tectonic plate slides beneath another. Unlike typical earthquakes, which involve sudden rupture, these movements are slower, often described as a form of gradual slipping that releases energy over extended periods. Recent counts of these tremors have reached into the hundreds per day, with cumulative totals exceeding several thousand over the course of a week. This level of activity reflects a significant amount of motion occurring along deeper sections of the fault system. While these tremors do not produce the sharp shaking felt during conventional earthquakes, they provide critical insight into how stress is being distributed beneath the surface. The interaction between these deeper tremors and the offshore earthquake swarm introduces an important dynamic. In some sections of the fault system, energy is being released gradually through slow slip processes. In others, it is being stored, building up over time. The boundary between these zones is not fixed. It shifts as conditions evolve. Areas that are currently slipping may transition into locked states, while locked sections may begin to release strain. This contrast between slow and locked behavior is central to understanding the broader seismic risk. When stress accumulates over long periods without release, it increases the potential for a large-scale rupture. Conversely, areas that experience frequent small releases may reduce the likelihood of sudden, large events, though they do not eliminate it entirely. The coexistence of both behaviors within the same system creates a complex and interconnected network of stress transfer. Further complicating the picture is the influence of adjacent fault structures. South of the primary offshore activity lies a major fracture zone characterized by lateral or strike-slip motion. Movement along this zone can redistribute stress across the region, affecting both the spreading center and the subduction interface. This interconnectedness means that activity in one area cannot be viewed in isolation. It must be considered as part of a larger system where forces are constantly interacting. The historical context adds weight to the current observations. Geological records indicate that the subduction boundary connected to this offshore system is capable of producing extremely large earthquakes. These events do not occur frequently, but when they do, they release immense amounts of energy. Evidence from sediment layers, coastal land changes, and other geological markers shows that such earthquakes have occurred repeatedly over thousands of years. The interval between these major events is irregular, but patterns can be identified over long timescales. In the past, gaps between large earthquakes have varied, sometimes spanning several centuries. The present interval has extended beyond 3 centuries, placing it among the longer gaps observed in the geological record. While this does not indicate that a large event is imminent, it does highlight the amount of time over which stress may have been accumulating. In addition to offshore activity, smaller earthquakes have been detected deeper within the continental margin. These events occur near the boundary, where the descending plate interacts with the overriding plate. Their presence suggests that deformation is not limited to the oceanic environment, but is also affecting regions closer to land. Clustering of these deeper earthquakes over recent weeks indicates ongoing adjustments within the system. The offshore swarm, when viewed alongside these deeper and broader patterns, forms part of a larger picture. It is not an isolated anomaly, but one component of a multi-layered process involving plate movement, stress accumulation, and energy release. Each tremor represents a small adjustment, a minor shift within a system that is constantly evolving. The uniform depth of approximately 10 kilometers, or about 6.2 miles, remains one of the most consistent features of the sequence. This suggests that the earthquakes are occurring within the oceanic crust rather than deeper mantle structures. It also indicates that the stress being released is concentrated within a specific mechanical layer where conditions are favorable for brittle failure. The offshore tremor sequence gains deeper significance when placed within the full geological framework of the Pacific Northwest, where multiple tectonic systems converge and interact over immense spans of time. Beneath the surface of the Pacific Ocean, the crust in this region is neither uniform nor static. It is segmented, fractured, and continuously reshaped by the motion of tectonic plates that move only a few centimeters or roughly a few inches each year, yet collectively generate forces capable of reshaping entire coastlines. At the center of this activity lies the Juan de Fuca Ridge, a submarine mountain chain formed by seafloor spreading. Here, molten rock rises from the mantle, filling gaps created as tectonic plates diverge. As the magma cools, it solidifies into new oceanic crust. This process occurs continuously, creating a conveyor-like system where newly formed crust is gradually pushed away from the ridge axis. Over time, this crust travels eastward, moving toward the boundary where it will eventually descend beneath the North American plate. The earthquakes recorded in the recent swarm are closely aligned with this spreading environment. At depths of approximately 10 kilometers, or about 6.2 miles, the oceanic crust is still relatively young and thermally active. Heat from the underlying mantle keeps the rocks more ductile than older, colder crust. Yet the upper layers remain brittle enough to fracture under stress. This combination of heat and mechanical tension creates ideal conditions for repeated seismic events. As the crust moves away from the ridge, it begins to cool and contract. This cooling process introduces additional stress as the material becomes denser and more rigid. Fractures develop, faults form, and the crust becomes increasingly segmented. These weaknesses can act as pathways for seismic activity, allowing stress to be released in localized bursts rather than through a single large rupture. The clustering of earthquakes within a confined area suggests that such a network of fractures is actively adjusting in response to ongoing forces. The geometry of the ridge itself also plays a role. Spreading centers are not perfectly straight. They are offset by transform faults that accommodate differences in plate motion. These offsets create zones where lateral movement occurs, adding another dimension to the stress field. In the region off Washington, the interaction between spreading segments and transform structures contributes to a complex pattern of deformation. Earthquakes within this environment may reflect not only vertical adjustments related to crust formation, but also horizontal shifts along these connecting faults. As the newly formed crust continues its journey, it approaches the Cascadia subduction zone, one of the most significant geological boundaries in North America. Here, the Juan de Fuca plate is forced beneath the North American plate in a process known as subduction. This boundary is not a simple line, but a broad interface that extends for hundreds of kilometers or several hundred miles along the coastline. The mechanics of subduction introduce a different set of conditions. The descending plate bends and flexes as it is pulled into the mantle, creating zones of compression and tension. Sediments accumulated on the ocean floor are scraped off and piled onto the continental margin, forming an accretionary wedge. Beneath this wedge lies the locked portion of the fault, where the two plates are pressed together and resist movement. It is within this locked zone that stress accumulates over long periods. Deeper still, conditions change once again. Increased pressure and temperature alter the physical properties of the rocks, allowing them to deform more slowly. It is within this deeper environment that tremor activity and slow slip events occur. Unlike the sharp rupture of typical earthquakes, slow slip involves gradual movement along the fault, often taking days or weeks to release energy. These events are not directly felt at the surface, but they can be detected through sensitive instruments that measure subtle ground motion. The recent increase in tremor counts across the broader Cascadia region suggests that this deeper portion of the fault is actively adjusting. Daily totals reaching into the hundreds indicate sustained movement, while weekly counts in the thousands reflect a significant amount of cumulative slip. This activity is not evenly distributed. It tends to concentrate in specific regions where conditions favor this type of deformation. The relationship between slow slip and the locked zone above it is critical. When deeper sections of the fault move, they can transfer stress to shallower regions that remain stuck. This process does not immediately trigger large earthquakes, but it alters the stress balance within the system. Over time, repeated episodes of slow slip can influence when and how the locked zone eventually releases its accumulated strain. The offshore swarm near the spreading ridge adds another layer to this interaction. While it occurs at a considerable distance from the subduction interface, it is still part of the same tectonic system. Movement along the ridge affects how the plate behaves as it approaches the subduction zone. Variations in crustal structure, temperature, and composition can influence how stress is transmitted across the plate. One important factor is the age of the oceanic crust. Younger crust, such as that formed near the ridge, is warmer and less dense. As it moves away and cools, it becomes more rigid and capable of storing greater amounts of stress. The transition from warm, ductile material to colder, brittle crust creates gradients that can concentrate stress along certain lines. These gradients may play a role in determining where earthquakes occur and how they propagate. Another key element is the presence of fluids within the crust. Water trapped in sediments and rocks can be released as the plate is subjected to increasing pressure during subduction. These fluids can migrate along faults, reducing friction and making it easier for movement to occur. In some cases, fluid pressure can trigger earthquakes by weakening the rocks along fault planes. The interaction between fluid movement and seismic activity is an area of ongoing study, but it is widely recognized as an important component of subduction zone dynamics. The historical record provides additional context for interpreting current activity. Geological evidence indicates that the Cascadia subduction zone has produced massive earthquakes in the past, with magnitudes reaching approximately 9. These events are inferred from a combination of offshore sediment deposits, known as turbidites, and onshore indicators such as subsided coastal forests and tsunami deposits. Together, these records form a timeline of past ruptures extending back thousands of years. Analysis of these records shows that the intervals between major earthquakes are not uniform. Some gaps are shorter, while others extend for several centuries. The current interval, now exceeding 3 centuries since the last known full rupture in 1700, stands out as one of the longer periods without a major event. Over the past several thousand years, this duration ranks among the longest observed, suggesting that a significant amount of strain may have accumulated. However, the system does not operate on a simple schedule. Variability in plate motion, changes in stress distribution, and interactions between different parts of the fault all contribute to the timing of large earthquakes. The presence of ongoing seismic and tremor activity indicates that the system is active, but it does not provide a precise timeline for when a larger event might occur. The offshore swarm, while moderate in magnitude, reflects active deformation within the oceanic plate. Each earthquake represents a small release of energy, a minor adjustment within the crust. When considered collectively, these events provide insight into how stress is being distributed across the region. The fact that they are occurring in a concentrated cluster suggests that a specific segment of the crust is responding to localized forces. Comparisons with past activity reveal that similar swarms have occurred in other parts of the ridge system, but the current location has seen relatively little activity in recent decades. This makes the sequence noteworthy, as it may indicate a change in the behavior of this segment. Whether this change is temporary or part of a longer-term trend remains uncertain, but it highlights the importance of continuous monitoring. Further south, the Blanco fracture zone introduces additional complexity. This region accommodates lateral movement between segments of the plate, creating a network of strike-slip faults. Activity along this zone can influence stress distribution, both along the ridge and toward the subduction boundary. The interconnected nature of these systems means that changes in one area can have effects that extend far beyond their immediate location. The broader tectonic setting can be visualized as a system of interconnected components, each influencing the others. The spreading ridge generates new crust and introduces extensional forces. The fracture zones accommodate lateral movement and redistribute stress. The subduction zone consumes the oceanic plate, storing and eventually releasing energy in large earthquakes. Overlaying these processes are the effects of temperature, pressure, and fluid movement, all of which shape how the crust behaves. In this context, the recent wave of tremors is not an isolated anomaly, but part of an ongoing process that has been unfolding for millions of years. The forces driving this activity operate on timescales far beyond human perception, yet their effects can manifest suddenly and with significant impact. Understanding these processes requires careful analysis of patterns, both short-term and long-term, to identify how different elements of the system interact. As data continues to accumulate, the focus remains on identifying changes in behavior. Variations in earthquake frequency, magnitude distribution, and spatial clustering can all provide clues about underlying processes. Similarly, changes in tremor activity and slow slip patterns offer insight into deeper parts of the fault system that are not directly observable. If you found this deep dive informative, do not forget to like, share, and subscribe, and tap that hype icon to help this video reach a wider audience.